We will continue the embedded system design class, and today we will talk about the asynchronous serial communication. So, um, uh, we will talk about in the outline the parallel versus serial communication, the asynchronous versus the synchronous wave communication, the receiver input sampling, how is this happening, and then we will follow by a discussion in the UART module of the BIC24 microcontroller, and we will give at the end an application, which is the receive ping pong example. It's a little bit more complex than what we've studied before. You would notice that the coding of this example is a little bit long. However, you can manage it. So let's start. When we say parallel I/O, we mean that the data sent over a group of parallel wire. As you can see here in this bus, we have 16 bits. The data is traveling from CPU1 to CPU2 in a group as a group of parallel wires of 16 bits. Typically, a clock is used for synchronization. If we use a clock, then this will be a synchronous wave communication. This is, as you see here, we have a clock generated by CPU1, and it is sent to CPU2 to organize the way of the communication. This is a question to understand how the parallel communication works and the effect on bandwidth. If a 16-bit data is transferred each rising clock edge, and the clock rate is 300 megahertz, what's the data transfer rate? The data transfer rate, we call it the bandwidth. So this bandwidth is required in bytes per second. That's the unit, the required unit. So since we have 16-bit data, if you divide it by 8-bit, that's 2 bytes. Now for 1 byte, to transfer 1 byte, we need 1/300 meg. That's the amount of time that you need to transfer a single byte. Now, the bandwidth would be the number of bytes divided by the time to send a single byte. Or you could say that's the number of bytes divided by the clock period. And now we know that the number of bytes, since it's 16 bits, that's 2 bytes divided by this amount of time, which is 1/300 meg. And that will give us the bandwidth, which is 16 or 600 megabyte per second. And be careful of the unit. Sometimes we measure it megabyte per second or megabit per second. It depends on the situation. So since he required it to be in bytes per second, this is the result that we have. Now let's compare this to the serial I/O. So the serial I/O, the data sent 1 bit at a time. So you send the data bit by bit over a single wire. You can see that now we don't have a bus anymore. It's actually, you could say it's a bus, but it has only a single bit per clock that you can move from CPU1 and transfer it to CPU2. Same thing, you could use a clock for synchronization. Now let's have the question again. Now, assuming 1 bit, only 1 bit, that's a serial communication, is sent each rising clock edge. How fast does the clock have to be in order to achieve the 600 megabyte per second that we just got in the previous example? So I'm detailing everything to make it simple to understand. Convert the byte per second to bit per second, since the serial communication is managed bit by bit. So 8 bits in 1 byte, we have 600 megabyte per second. That's 600 megabyte per second. If we multiply it by 8 bits for a single byte, now you can take out the byte with the byte, and you end up with 4,000 800 megabit per second. Now, the megabit per second, we can say that this is actually the hertz. The bit per second is the unit hertz. That is for the frequency. So 4,800 mega is actually 4.8 gigahertz. And that would be the clock frequency. So to send the same amount of data, you need this high frequency, which is 4.8 gigahertz. If you do the communication bit by bit, compare that to only 600 megabyte per second if you do it in parallel, 2 bytes in each clock. So to formalize this comparison, we have the parallel I/O and the serial I/O. The advantages of the parallel I/O is speed. The bandwidth can be increased by either making the data channel wider, so you transfer more bits per cycle, or you increase the clock frequency, obviously. For the serial I/O, now the disadvantage for it is actually the advantage of the parallel, which is the speed. It's actually slow. The serial I/O is slow. So the fastest serial link have lower bandwidth than the fastest parallel link in comparison. For long distances, let's say meters, new fast serial I/O standard have replaced the older parallel I/O standards. So now the serial I/O is coming back to the picture. And the famous one is the USB. We have USB 2, USB 3. We have the FireWire or SATA and so on. Now, what about going back to the parallel I/O? The disadvantage for the parallel I/O that it is actually expensive. Wires cost money, short. So this is why we use it only for short distance only. The long parallel wire cause crosstalk and data corruption and many other things if you try to make it for long distances. Now, this disadvantage for the parallel I/O is actually the advantage of the serial I/O, which is actually the serial I/O now is cheap. It has very few wire needed. For example, the USB needs at most 4 wires. It's good for long distance interconnect. Now, the way of communication differ from one way to another. We could say that we have, in terms of communication channel, we have the simplex communication, the half duplex communication, and the full duplex communication. Now, the simplex communication, it's actually communication in one direction only. So you specify the direction. One of the entity would be the master, which is CPU1, and the other would be the slave. That's the simplex way of communication. Now, the half duplex, the communication could happen in either direction. In either direction, however, it's only one way at a single cycle. So if you have, let's say, 2 cycles, one cycle would be for this direction, the other cycle for this direction. And so if you have many cycles, you could alternate or do it in different ways. Now, for the full duplex, the communication is in both directions, and it could happen at exactly the same clock cycle. So let's say a phone call as an example. For the half duplex, if you are a speaker and the other guy is the listener, you speak and he listens. That's one direction. And then once the talk is over in a certain subject, you exchange the roles. He becomes the talker and you become the listener. And you do this back and forth, and so on. For the full duplex, and this will be a little bit weird for a phone talk, if both of you talk at the same time and listen at the same time, then that's a full duplex. Now, for the wires, the simplex wire, the communication occur in one direction, and now we give it names. We have the transmitter or the TX, And usually you have a buffer to show the way that it is this way and you cannot do it in the other way. It's a unidirectional. So this will be the transmitter all the time. And this will be the receiver or RX all the time. For the half duplex wire, we actually discussed this when we talked about the GPIO. Now the communication can occur in either direction. So here you have an output enable, and this will be a transmitter. This unit will be the transmitter this way, and the other one should be the receiver. So this is the transmitter, and this is the receiver. Now, if you want the other direction, now this will work. Of course, this will be disabled, and the output enable will make this buffer enabled. This one will be the transmitter, and the other one would be the receiver. We talked about this when we talked about the GPIO. To make this board an output port, you make its stress value active low, which is 0. And the other one, the stress will be equal to 1 to make it input. That's the discussion that we had before. Now, let's talk about the synchronous and the asynchronous serial I/O. Now, we will fix the way of your communication to make it serial. So there is no parallel communication. Everything is bit by bit. And we want to see what is the synchronous and the asynchronous serial I/O. So here in the synchronous serial I/O, we have 2 units. Let's say here it's CPU1 or CPU2. When we say CPU2, it could be a microcontroller, and inside this microcontroller, there is a microprocessor, right? We've seen this many times. So since it's synchronous, you need an internal clock between them. This internal clock, it has certain frequency. It has also a tolerance value. They could differ with a certain percentage, and still it works fine. But they can be out of phase, where you need to resynchronize the clock. So the synchronous serial I/O either sends the clock as a separate wire. So you have a wire specialized for only sending the clock. So you dedicated that wire for sending the clock only. Or the receiver, the CPU2 in this case, extract the clock in different ways. There are many ways to extract the clock from the message itself, from the data stream itself. So you send bit by bit, and from this stream of bits, you can extract the clock from that, or you use what they call the phase alignment using the PLL. And we talked about the PLL. Remember, we said that one functionality for it in the oscillator, it boosts up the frequency. It also align the clocks. For this other method to work, you must have transition density. You can't have this the data 1 for a very long time, logic 1, or logic 0 for a very long time. This way you don't see movement of the data. So you need transition density, which means the data line must be guaranteed to have minimum number of stages or changes, state changes, from 0 to 1, which is the rising, or 1 to 0, which is the falling within a particular time interval. For the second method, you need transition density, and this is used actually in the USB. The synchronous serial I/O can achieve high speeds, and this is why you can see them and you work with them. And you can see many types of them. The USB, the one that you know, this is called type A. We also have type B. You might have seen this in printers or USB hubs and things like this. There are many others like the mini A, mini B, mini AB, and there are many other types like type C and so on. That's for the synchronous serial I/O, and the bottom line here, you need a clock. For the asynchronous, the CPU1 and CPU2 send only the data, and the asynchronous serial I/O does not transmit the clock on a separate wire, nor does it guarantee a particular transition density. Now the data, then how to manage this? How the sender the sender will send the data. How the receiver knows that this data is actually something that the sender transmit to him. So for that, the data line could remain in the same state, either 1 or 0 for the duration of the transmission after the initial state change indicated the start of the communication. The key word here is the start of the communication. So you need a way to for the receiver knows exactly where, when did, or what is the start of the piece of information that the transmitter sent. This piece of information, we usually call it frame. So you need the start of the frame, you know, exactly to know, or the receiver needs to know when exactly is the frame started and when exactly it is ends. So the asynchronous serial I/O is used for older standard. It is easy to implement, but it is slower than the synchronous serial standards. That's for the asynchronous. That's an example of the three-wire asynchronous serial interface. This is actually used in old screens, and the replacement for this is the HDMI cables. The three-wire asynchronous serial interface is used to connect the BIC24. It could have been used to connect the BIC24 to an external PC. So a connection between your laptop or PC and the microcontroller could happen using this way. This way is actually a standard, and it is known as the RS-232. There is another way that we are working on in the lab, which is using the snap, and we've talked about this when we talked about the GBIO lecture a long time ago. Now there are here, well, we are interested only in 3 wires, but there are actually more wires defined in the standards. The 3 more wires or the 3 wires that we will focus on, 2 of them is very obvious, the transmit. So if this guy is transmitting, there is a dedicated wire for it, and the CPU2 is receiving that, or it's vice versa. The CPU2 transmits and the CPU1 receives. The third wire is a reference ground signal. You must have a ground signal. Now, in the standard, this is actually the standard, and it has many pins. Actually, you have here 1, 2, 3, 4, and 5, 6, 7, 8, and 9 pins. So let's find the 3 wires that we are interested in. We have the receive, we have the transmit, which is pin 3, pin 2 is the receive, pin 3 is the transmit, and we have the ground. Other than that, there are status wires that could be used, like the request to send, the clear to send, and we have ring indicator, we have the data set ready, we have also the data terminal ready, and we have the data carrier detect. You can see from their names that they are used for status and making sure that the communication is happening without errors, like certain acknowledgement, and we will see them, some of them will see them in action when we talk about the UART. So from this discussion, each wire is simplex, but the communication altogether is actually could be full duplex. Now, we said if you have an asynchronous serial communication, you need to know the start and the end of this piece of information that you are sending, which we'll call the frame. So there are actually 3 types of frames. The first type is a 10-bit frame with 1 start bit, the start bit that you can see here, 7 data bit from D0 to D6, 1 parity bit, this is the parity bit that could be even or odd, and 1 stop bit. And now you have a full frame from the start to the stop bit, and then another frame starts. The way to call it in short is 8, even, odd, 1. 8 means you have an 8-bit for the data. Even and odd, it means that one of these data is actually parity. So you have from 0 to 6 data and 1 parity. You know it only from this. And you have 1 here. It indicates that you have only a single stop bit. Now, it's very important to know that for this way of communication, the start bit is low, is a low signal. So the receiver, the transmitter need to abide by this rule, and the receiver always look for a low signal. And after the low signal, he knows that this is the start bit. So it should be 1 for a very long time. And then you have a pulse, which is a low pulse. This low pulse tells the receiver that, hey, there is a frame about to be starting. And then you have the data, and at the end you have a stop bit, which is actually a high value, and it will remain high for maybe only a single bit cycle or for a longer time, and then you will have another start bit and so on. So that's one way, which is the 10-bit frame. The other way is also a 10-bit frame, but now we don't have a parity bit. We dedicate all the bits for data. So instead of 7, now we have 8 from D0 all the way to D7. And same thing, you have a start bit. Now you have 8-bit, all data, and then stop bit, and then you do this again. And it is called 8, N, and 1, N for saying that we have no parity. We also have the 11-bit frame, and now we are adding one more bit. It has 1 start bit, a data bit, and no parity, but it needs 2 stop bits. 2 stop bits to make sure that the stopping point is always read by the receiver. This is for, like, we are giving this, the 11-bit frame, we give it more guard at the end to make sure that you read it in case this wire is affected by noise or things like this. And then another frame starts, and it is called 8, N, and 2, and you can see the difference. Now we have 2 stop bit. Now you should know, for this way of communication, you send the least significant bit first, and it is also read by the receiver first. So the least significant bit, and then followed by other bit until the most significant bit of the data. Now, just to revise what you've known regarding parity, a parity bit is an extra bit added to the data frame to detect single bit error. It detects only a single bit error. A single bit error is 1 bit of the frame received incorrectly. This way we call it a single bit error, only a single bit. It's read as 0, for example, when it should have been 1, or vice versa. For multi-bit error, there is no guarantee to detect it using parity. There are other methods like the CRC, and there are many other error detection methods. But here, for this asynchronous serious communication, we are only interested in the parity. It's enough for us because usually we do this in a short distance. We are talking about a microcontroller within a system, so the communication would be short distance. Now, this parity could be odd parity or even parity. We just define this with examples. Odd parities, the parity bit value makes the total number of one in the frame odd. So, for example, for a 7-bit data value, let's say it's 0x65, this is a 7-bit. The 6 in binary is 0110, and the 5 is 101. You can see, you can count them, they are only 7 bits. Now, to add a parity for this, count the number of ones. So 1, 2, 3, 4. This is even number. So we need to make the odd parity equal to 1. So the number of ones, when you count them, they become 5 which is actually odd number. That's the way to implement the odd parity. The even parity, but the definition here, instead of odd, it's even. So parity bit value makes the total number of ones. We're counting the number of ones in the frame, even number. So for this 7-bit data value, now we have 4 ones. That's an even number. So we will make the even parity 0. So we keep the number of ones still even, which is equal to 4. Let's give more examples so you understand what's going on and how to implement this way of communication. Let's say you have this data. This is sent as 7 data bit. So this is 7 bits, odd parity bit and 1 stop bit. This is the way we want to send it. So you must have a start bit, which is the low, and then you send the least significant bit first. So you send the 1 first, followed by the 0, followed by the 1, followed by the 1, and so on, until you reach to this bit. Now you send 7 bits. Here we said we will have odd parity, so count the number of ones. The number of ones here, actually, they are even, so you need to make the odd here equal to 1, followed by 1 stop bit, and then you have another frame. This way we send this information. This information could represent a part of an instruction, part of a data. It could be any. Now, this example, same one, the only difference here is we change the parity. Now the parity is even. This slide number 14, so let's compare it back to slide number 13. You see the difference here is only the parity. Now for the even parity, the value here is equal to 0. Next example, we have now 8 data bit. There is no parity and 1 stop bit. So we just copy the data from the least significant bit and so on until you reach to bit number 7, which is this one. So let's count from 0. So we follow the engineering way. So this bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, and this is bit 6. And this one is bit number 7. And the total from 0 to 7 is 8 bits. And so on. Now you will, this is, let's say we generated this in the transmitter and we send it to the receiver. So the receiver should look for the start bit. Once it knows that this is the start, it start accumulating the bits. Now, how did the receiver read this bit? Does it read it here, or here, or here, or here? The receiver needs to decide. And this is what we called the receiver sample. So if we take only 1 bit time, that's a single bit of the 8 bits, let's say, of the data, or the stop bit, or the start bit, any bit. If you have 1 bit time, the receiver clock or the period is either 4 times the bit time or 16 times the bit time. So you can see here, shown here, we have the receiver sample with 16 clocks. So the receiver will have a clock to read the bit, to just read the bit. So you can see that we have 16 clock from 0 to 15, and it should sample in the middle. So you make sure that you are reading the value in the middle. So at the start bit, an internal 4-bit counter, because we are counting from 0 to 15, we need 4-bit counter. You start from 0 and then you start 0, 1, 2, 3, and so on. The data is sampled at the midpoint of the bit time, which is the mid value, which is, you could say 7 or 8, one of them. But most, they prefer number 8, but you could work with 7 as well. So this counter starts 0, 1, 2. So at the moment you have any change, let's say that this is the start bit. So since it is low, now the counter start counting 0, 1, 2, 3, 4, 5, 6, 7. If it reaches to 7 or 8, now it samples the bit and it reads its value. The receiver only accepts the bit if all the values are the same for the glitch rejection. If it wants to make sure, the receiver could read 7, 8, and probably 9. So it makes 3 reading and they should all match. So if they match, it will accept the value. The receiver or transmitter clock are not perfectly matched. We have tolerance value for it. It's about half the bit time or the 50% of the bit time spread over the entire frame. So if this spread, now you have an entire frame, which could be 10 bits or 11 bits, assuming that we are using the 10-bit frame, the maximum mismatch between the RX, the receiver, and the transmitter clock is this 50% for a single bit divided by 10 bits. That's the whole frame, which will be equal to 5%. You could have this mismatch. Now let's have an example. So let's say in this example, you were asked to give the maximum bandwidth in bytes per second for an asynchronous serial link operating at this amount, which is 115,200 bit per second. So that's actually the bandwidth. You could say it's the frequency. Assuming you have 8 data bits, 1 stop bit, and no delay between the characters. Since you have 8 data bits, for sure there is no parity. So you will have 8 data and 1 start and 1 stop. Notice if you go back, for all the types, these 3 types, you always have a single start bit. This is why we didn't even mention it here. You always have a start bit. So you should account for it. Don't forget that. So you have the 8 data, single start and a single step. That's 10 bits divided by the speed or the frequency of the bandwidth. You could say any of them. So if you divide that by the amount, you would have this time, which is the transfer time for a single byte. Now the data here is single byte. So now the bandwidth in bytes per second is the reciprocal value of this one. This is the required. What is the maximum bandwidth? And this would be the maximum bandwidth. Now, after this introduction, we will move to the UART module. And you will see many of the things that we discussed here, you will see it, you will see that we need to set it up for the UART to work. So, the big 24 microcontroller UART-X. So you could have UART1, UART2, and so on. In our class, we will only use UART1. Now, the UART is short for Universal Asynchronous Receiver Transmitter. So we know that the UART is used for communication. There is a sender and receiver. We also know that it's asynchronous, and we also know it is serial. So the hardware module that it implements asynchronous serial I/O. It's referred to as UART-X, as there might be multiple UARTs, as we've said. And in this class, actually, we will use the 8-bit with no parity. So now you know the types, and we will always use 8-bit with no parity. There are actually, these types will be listed when we talk about the special function register. So here, as you can see, that's the UART receiver and the UART transmitter and some of other logics that it might need. So the receiver actually receives in the UXRX, so maybe U1RX, so you receive here. If you go and check the pin diagram of PIC24, you won't find this pin, so you need to use the remappable pins again. We have a UART transmitter that transmits bit by bit. We call it UXTX. And you have other logic that organize the wave transmission but it's actually more like optional if you want to use. You could use the hardware flow control where you have a request to send or a clear to send signal. And we have seen this when we talked about the RS-232 standard. Notice that they are active flow. So when you want to transmit, you should actually wait. You could have a flow control that helps you to know if the receiver is ready for you or not. So you are transmitting to a receiver somewhere. To have some piece of information back from the receiver that tells you that make the receiver tells you, hey, I'm ready for you, command transmitter, start transmitting. This signal would be the clear to send. The receiver would tell the transmitter, hey, you're clear to send. Come on, let's go. So it will start transmitting. Similarly, you have the same scenario between the receiver and the request to send. That's called the flow control. If you study a communication course, they will talk in detail about this. We have also the IRDA. That's the Infrared Data Association standard for communication. And if you want to use it, it's an option. And you also have the baud rate generator. For any UART module, you need to identify the bandwidth at which you are transmitting or receiving based on the baud rate generator. So we have UART register to facilitate the communication. From what we've discussed now, we know that the most critical is the receiving and the transmitting hardware. So in the transmitted hardware, you have a transmitting register that is connected to the internal bus of the PIC24. And from the internal bus, you send the data that you want to transmit to this register. And there you go, you transmit on the line asynchronously and bit by bit, meaning serially as well. Same thing for the receiver. Once you receive any data bit by bit, you store it in the receiver register or the U1RX register. So we know that these two registers, one for receiving and one for transmitting. We also have a U1 stat or the status register and U1 mode that have the control fields that specify the way you work with the UART. So they both contain configuration bit and the status bit for the module. And we have a dedicated register for the baud rate. You set the baud rate, or this baud rate will dominate the communication. It will tells you exactly what is the bandwidth that you should use. So just let's use the correct terms. So the baud rate is actually a unit of measurement of the same baud rate to determine the speed of communication over a data channel. So let's have an easy example and a more realistic one. The easy one is if you say the bit per second is exactly the baud rate. So when you're sending something, you send it, your baud rate would be bit per second. This means that a single sample is actually 1 bit. So you send one sample, which is equal to 1 bit. So this way of sampling, or this way of sampling, you would make a 0 indicating you have a 0 volt, and 1 indicating you have a 5. And that's it. You have two ways to distinguish between two different values. If you increase the baud rate, for example, bit per second is actually twice the baud rate. So this means that one sample contains 2 bits. So now you have 0, 0, 1, 0, 0, 1, and 1. And you specify for each one of them the voltage value for it. So in this case, we say that 0, 0 is 0 volt, 1, 0 is 5 volt, 0, 1 is 10 volt, and 1, 1 is 15 volt. This is what we mean by the baud rate. So now let's talk about the hardware of the transmitter, followed by the hardware of the receiver. So in general, you have a bus and you want to transmit. So from the bus, you want to move and transmit bit by bit asynchronously into this pin. This is the goal. So to do this, you have actually a 4-entry FIFO or a queue that you can store only four frames ready for transmission. And you also can have one more in processing, transmitting right now in the transmit shift register. So total you have 5. A frame ready for transmitting in the shift register, and waiting in the queue, there are 4 frames. That's the maximum. So let's say you have 5 frames that you want to send. You will get it from the bus and you will put it in the FIFO. The FIFO is empty. So right away you put it in the transmit shift register. Now here it will transmit bit by bit, and it would use a clock to organize this way of transmitting. And then the second frame comes while you are still pushing only maybe 2 bits or 1 bit. Already a frame is coming. You cannot overwrite it, so you put it in the FIFO. Next one, you put it in the FIFO. Next one, you put it in the FIFO. And the last one, you put it in the FIFO. And now your FIFO is full, and probably you are in the middle of communication or in the middle of transmitting this frame in the shift register. Now, again, we use the same thing. We start bit, we have data bit, and then stop bit, and so on. And that's why you have this multiplexer, where either you remember, this is only data here in the shift register. So you need to generate the start bit, and then followed by the data, and then maybe a parity, and then followed by a stop bit. That's one way to send the frame. Remember, sending the this frame in the shift register, if you send the data, you would start by the least significant bit first. Now, who dominates all of this, or who controls this operation? You have a transmit control. You have many signals actually that can help you identify everything in this hardware. So you would have 2 special function register, one for the status and one for the mode, specifying everything. How many stop bits you have, do you have parity or you don't? Do you want to use the flow control bits, the clear to send or request to send or not? What kind of sampling in the receiver? Is it 16x or 4x? These kind of things are mentioned here. And to check the status while you are transmitting, you could consult the status special function register. That's the transmit control. It has other functionalities as well, like these buffers that you see here. here in this queue, it could be only from 0 to 7. You can make it from 0 to 15. So here in this buffer, either you choose word or byte. There are choice. Either you use only byte or the whole word. And this buffer only if you use a word. If you use from 0 to 15, then you will supply the data over here for the FIFA. Also here, for this buffer to control it, you have this signal. And you also have a flag. The flag is the transmitter interrupt flag. You might generate an interrupt for the processor inside the microcontroller if you want to use interrupt-driven way of coding or the interrupt-driven IO. Also, as you can see here, this is a 16 divider. This is for the 16x baud clock from the baud rate generator. And this is a parity generator as well. If you use flow control, the transmitter should expect clear to send from the receiver. Anything that comes as an input should be first accepted by Schmidt buffer. So you make sure the edges are sharp because maybe you will have noise or something like that. This is the way of the transmission. Also, some of the details here, you can use the UTX break, so the transmission break. If the break is equal to 1, after the inversion to be 0, so the value is going to be 0 and everything breaks down. And there are many other details actually that we are not showing here. So the idea of the transmitter, I believe it's clarified to you now. The receiver, again, the general idea here, from the receive pin that you must use removable pins for it. You are a receiver now, and the data is coming to you here. And then you should ultimately put it in the bus, so the microcontroller CPU could work on them. Same way, you have a receiver shift register. There is a Schmidt buffer because what's coming from outside, so you don't know, maybe it has a noise. You sharpen the edges and you go to the shift register. Again, least significant bit first and then the most significant bit of the data. And then here you store while, let's say, you are receiving many frames, you also have a FIFO that stores 4 frames. So maybe the bus still needs to work on some values or doing some other job. You can store the frames here, 4 frames and 1 in the shift register, and you can push it into the data bus one by one when the CPU is ready. Now, same way. There are so many things that needs to control this process, meaning the receiving process. So again, you have the mode special function register and the status shift register, which should follow the same one as the transmitter. And you could actually make a test run using the loopback. So your own microcontroller has the transmitter and the receiver. So you connect the transmitter to the receiver directly without going to an outside receiver. And you use the loopback. So from the internal transmitter of the same microcontroller. And you could use something from the outside. This is always used for testing. So maybe you do the testing first to make sure that everything is fine, and then you do communication with another outside entity. You have also some status error checking. We have the P error or the parity error, the frame error. You have overflow and many others, all of them for checking. So you need the receiver controller. This is hardware. They are responsible for many things like generating the flag, generating the interrupt, shifting the data characters, and so on. And also they generate they receive interrupt flag. When you receive something, the CPU is usually busy doing something else. Once it shows or it sees the interrupt flag, it means that there is something being received in the the receiver shift register. Yeah, other things you can see here, these buffers have control values. So here, if you use word, this is for byte or a word, so you have control over this. You also have the control for this buffer to move from the shift register to the queue. And the receiver uses the sampling that is generated by the baud rate generator. And if it is 16x, it's responsible for sampling each and every one of the bits that you are receiving. Remember, this is serial reception. So you receive bit by bit and you should sample in the middle of the bit. So there is a hardware that needs to detect the start bits to know that there is a frame which is coming. It detects the parity to check if there is a single bit error or not. Detecting the stop bit, shifting bit by bit. So you shift inside this shift register and many other functionality as well. Now, there are many options. You could use the flow control, or you might not use it. So we have the UART enable hardware. It's responsible for the selections, and there are 2 bits to control them. So you have 4 options: 0, 0, 0, 1, 1, 0, and 1, 1. Each one of them is specified in the mode, special function register, and we will see them soon. If you use flow control, then you should expect a clear to send signal, request to send signal, some clocking, and so on. Now, at this point, we kind of understand what is the transmitter and the receiver hardware. Now, your job is actually to program the microcontroller to use the UART module for communication. So you need to set up the mode shift register. You need to understand what kind of status bits that you need to worry about. So the receiver error conditions, we have the frame error. Frame error happens if the stop bit for a value was read as a 0 instead of 1. Remember, the stop bit is logic 1. So if it's read 0, that's a stop bit error. The parity error, if there is a single bit error, there is a wrong parity received. You are expecting an odd value and you received even, or vice versa. The overrun error, which means that there is no place to receive the new frame, and usually if that happened, we drop the frame. When exactly this happened? If the input FIFO has overrun, and this happens on the start bit of the 6th character. So you have actually, let's say frame, the 6th frame or the 6th character, same thing. So you have 4 frames in the FIFO and 1 frame in the receive shift register. The 6th is on the way and everything is full. Now you would have an overrun error. So the framing, the parity errors have to be checked before the character is read, as they match up with the byte that is currently available in the FIFO. Here's an example. Let's say, to understand what is going on, let's say we were asked to compute the maximum time before the UART receiver overrun. Given this baud rate, which is 38,400, and it's required to express this time in instruction cycle for frequency of oscillation 80 megahertz of the big 24, which is the maximum frequency. And this is the assumption of the frame. We have 8-bit data, 1 step bit, and no delay between characters. Now, the solution, the UART receiver can hold 4 bytes in the FIFO, we know that, and 1 byte in the shift register. In another way, we could name them frames, 4 frames in the FIFO and 1 frame in the shift register. So the total is 5 bytes. What is the time before the overrun? It would be 5 bytes. It's actually frame, not byte, but we just say 5 bytes. So there are 5 of them, 8 data plus a start bit plus a stop bits. That's total of 10 divided by this baud rate, which is 1.3, around 1.3 milliseconds. So the time for one instruction is 2 divided by 80 megahertz, and we know this with the relation between the frequency of oscillation and the frequency of instruction time, or the FOSC and the FCY. So 2 divided by 80 meg, that's 25 nanosecond. Now we can compare between them or find the ratio between them. The number of instruction cycle would be 1.3 divided by 25 nano, which is 52,080 instructions. That's what you would have. Now, let's talk about more of the things that you need to set up for the UART. So one of the important one is the baud rate generation hardware or the baud rate clock generation. We have a special function register for it. We said that it's called U1 BRG. This register is the period register for the big baud rate generation. And the baud rate would be equal to FCY divided by S times the BRG plus 1. So find the BRG first, add 1 to it, and then the total, you need to multiply it by S. That's the denominator. And then in the denominator, you have FCY. Where S, this value of S, it has 2 modes, either S equal to 16 or S equal to 4. Remember, that's the sampling of the receiver or the receiver sampling. So if you use 16 bits, that's a low speed mode. If you use 4, that's a high speed mode. You might be confused by this. That's 16 clock. How can we say low speed, not high? Remember, what we're interested on is in the bits themselves. So just to explain this quickly, if this is the start bit followed by certain data, let's say these are some part of the data, and then it continues, the frame continues. That's the starting bit. So, and if S is equal to 16, this means you would need 16 clocks here, and 16 clocks here, 16 clocks here, 16 clocks here, and so on. While 4, you would need only 4 in each one of them. So if you were asked which one will transmit the whole frame faster, the other one that requires only 4 bits or 4 clocks in each bit frame. This is why we call it a high speed. Now, usually you know your baud rate, you know your FCY, and you know your sampling. Usually we use 16. And you need to find the special function register value. This is why we'll rewrite this in this way. The U1 BRG is equal to FCY divided by S times the baud rate minus 1. So in a C function, if you want to write it, well, you could say or have an inline macro, as you can see here. This is the configuring baud rate, UART1, and you give it the baud rate, which is usually you should specify at the beginning. So one of the mode bits, which is U1 mode bits dot BRGH. For this bit, you choose it either 0 or 1. If it is 0, then it's low speed, which is the S equal to 16. If it is 1, then high speed, and this means S is equal to 4. Usually we make it 0, meaning S is equal to 16x. Now, for the BRG, you would say, okay, I will calculate the FCY, and I divide it by 16, since I choose here 0, so this will be 16, times the baud rate. The baud rate is given here, minus. Remember, this shouldn't exceed the 16-bit limitation. So, what kind of baud rate can I choose? Remember, this is an argument. So, can I put any number? Is there any restriction? We will mention them quickly. There is actually more discussion about this in any communication course. However, there are certain baud rates that you should choose. You should choose one of them. Either this one, 4,800, 9,600, the 19,200, 38,400, 57,600, and so on. These are the choices that you can make. And these two tables, one time we used frequency of oscillation, 80 megahertz from an internal oscillator with PLL. So we used it internally. And for this one, we used an external crystal with this frequency. So bottom line here, we used internal oscillator here, and here we use an external oscillator. So it says here, because the sender and receiver must both agree, you need a standard baud rates, one of them. So there is an agreement needed. So the sender would say, okay, I'll pick this one. The receiver should pick the same baud rate. Now you would see, if you check the errors here, you would see sometimes there are certain errors. Also the 2 or 3% inherent error. If you remember when we talked about the oscillator, when you choose the RC oscillator or the internal oscillator, you could have certain errors that with certain percentage. So this means that sometimes it is difficult to match higher baud rate, and this is actually shown here. In this table, so you know this information, and what do we mean by this? One time we use the high speed, so the BRGH is equal to 1, and other time we use the low speed, or the 16x. This is the 4x, this is the 16x. Which means the BRGH is equal to 0. So in the high speed, if you use an internal oscillator, we will have certain errors, certain percentage. Similarly, for the low speed, we will have certain errors. So you want the baud rate to be this value, but you are not actually getting this value here nor there. And you could see that when you decrease the speed of the baud rate, the frequency is decreasing here, then this error will also decrease because you are getting slow, which is actually expected. Now, if you use an external crystal, this is actually a kind of more tolerant to errors. So you want certain baud rate and you're getting exactly what you want, whether in the high speed or the low speed, which means it's better. At the bottom line here, if you want higher baud rates, use an external crystal, better for you. Now let's talk about the special function register. There are two special function registers that we need to start with. The first is the mod. So that's the control register. It has many fields to control the way of communication using the UART. And we have also the status register, or what we call U1 step. So U1 mode, you have many of them. I listed here only the ones that we care about. So we have the ST selector. Well, that's the stop bit selection. Either 1 bit or 2 bit, you select it this way in this field. Now we understand what do we mean by this. The parity and the data selection bit. So if it is now 2 bits here, so that's the parity and data selection. Either 8-bit with no parity, 8-bit even, 8-bit odd, 9 bits and no parity. These are all of the options, whether you use 10-bit frame or 11-bit frame. These are the options that you have If you use 000, this means it is 8-bit data with no parity. So purely data. And it's actually a good choice if you know that your system is contained, or your microcontroller is actually contained inside a system. So it's an embedded system here, and the distance is very short. So the error might not happen. The error rate is very, very small. The PRGH, actually the baud rate enabled bit, either 14x or 4x or 16x. So if the BRGH value is equal to 0, that's the 16x baud rate. If it is 1, that's the 4x baud rate. This is the slow and this is the high speed. This one is also the standard that we usually choose it. So up to this point, if you want to use the default value, it would have one stop bit, 8 data, no parity, and 16x sampling or receiver sampling. Now we talked about the UN. We talked about these two bits, UN 0 and 1. We talked about it when we saw the hardware of the receiver here, which is here. So you could say the same thing here. These are the UART enabled bits. If you choose 00, which is actually what we are going to use, it means you are interested only in the receiver and the sender pins. They are enabled. The clear to send, the request to send, and the B clock pins controlled by port latches. And actually, we are going to ignore them this way. If you use 10, then there are certain things that either if you use any other choice, 10 or 01 or 11, there on top of the transmitter and then the receiver, you can use the other flow control bits, as you can read. Now for the last one, bit 15, which is the UART enable bit, either you enable it or disable it. So if you actually disable the UART, that's it, you disable definitely. But if you enable the UART, now you need to check what is your choice here. So usually we'll enable the UART, make it 1, and we will make these 0, 0. We're interested only in the transmitter and the receiver pins. You can see there are other things that we didn't talk about, that are like the loop back and many others. You could go onto data sheet and consult it to understand these bits. But for our class, we will just focus on these. The status register, or the U1 status, you have many fields, as you can see. Some of them is clear to you now. You have the parity error, the frame error, the overrun error, and we talked about this. If the bit is 0, it means there is no error detected. Remember, this is status. All these bits are red here. If it is 1, then there is actually a problem, or there is an error. On top of that, we have the UART receiver buffer data available bit. This is red only. If it is 0, it means the receiver buffer is empty. There is nothing there. You are not receiving anything. If it is 1, it means the receiver buffer has data. At least one more character can be read. So there is something that you need to receive. You check this bit and it's 1. Oh, there is something that you are receiving. You have also the UART transmitter buffer full. The transmitter buffer, is it full or not? If it is 0, it's not full. If it is 1, then the transmitter buffer is full. If the transmitter buffer is full, then you cannot transmit any longer. You have to wait a little bit. And you have the U or the UART transmitter enable bit. Here, if it is 0, the transmit disabled. You don't want to transmit. Remember, the transmitter should initiate the transmission. So how does the transmitter say, okay, I want to transmit using this one? So if it is 0, the transmit disabled. Any bit in transmission is aborted. The buffer is reset. I'm not interested in transmission at all. If it is 1, transmitted is enabled, and then this pin, which is the transmission pin, controlled by the UART, and you can transmit now serially, bit by bit. There are other status bits here, but we only focus on these. And now we are ready to see the code, and we will show you the code in 2 methods. The 2 methods that we know, the polling method and the interrupt, and also the interrupt-driven method. We will start by the polling, followed by the interrupt-driven. In the polling, we first need to configure the UART. So we need to make the choices based on what we've just discussed. It was required to configure the UART with this settings. That we have the transmitter on RP11. So now we know the remappable pins for it. That's RP11. The receiver, RP10. The frame format is 8 data bit with no parity and a single stop bit. So we need to make the specification based on these settings. We have clear to send, request to send. All the flow control bits are not used. Also the B clock. And the FCY is 40 mega, or the FOSC is 80 megahertz. Now to set up the remappable pins, remember, we talked about this in the interrupt lecture. For the receiver, we would say underscore U1 RXR is equal to 10. So now we use the name of the receiver, and we make it equal to the remappable pin number 10. And for the transmitter, we use actually the code. The transmitter code is equal to, the receiver. Sorry, actually it's the transmitter. The transmitter code is equal to 3. And the remappable pin number 11 is equal to the code of the transmitter, which is equal to 3. For more information, go back to that lecture. Now we set up the UART. We use the mode bits, UART1 mode bits dot brgh equal to 0. That's the 16x, or the slow or the standard mode. The baud rate that we choose for this problem, based on the baud rate that you choose, remember the table that we discussed, you plug it in here, and we plug in the value of the FCY, which is the 40 mega, 16x, since we choose here 0, -1, and this is actually what we've seen in the macro that we just set it up, and the PRG value will be generated. Now for more mode bits that we need to set up, we have 4 more mode bits. The parity data selector is 0, 0, so it's 8-bit with no parity. The stop digit selector or stop bit selector is equal to 0. So we have 1 stop bit. Now we make the enables. We make the choice for the U enable 0, 0. So we don't need flow controls. We make the UART enable equal to 1. So we enable now the UART, both the receiver and controller. Since we enable it, we need to make this choice, and the choice we make it 0, 0. And for the transmitter, if you don't want to transmit anything, it should be 0. If you want to enable the transmitter, so now you want to transmit something, you make it equal to 1. This way we configure the UART. And we need this configuration for both the polling and the interrupt driven. Now we're talking about the polling. Now how to do the polling? We write in the main method the following. We just define the value B. So when we have something to receive, we put it into variable B, so it will be moved to the bus. And we configure the UART1 bullying, and we gave it this baud rate. We choose one of the baud rates in the table. This one is 19,200. And then we go through the while loop forever. And now here, the idea in the while loop, receive, just keep receiving. If you receive something, flip it only, do simple processing, and then transmit it again. We also need to check some flags to make sure they work done properly. So here we would say if F, check the status bit. Remember, when we are working, we need to check the status bit to make sure things are working fine. UART1 status bits dot URXDA. We use this bit if there is something in the receiver shift register. So if there is data available, take the data from the receiver register, and that's the important register that you need to check once you have received something. You get it from the register and put it wherever you want. We choose the variable B. Now what we want is we want actually to do some processing with B. Whatever processing is it. Here is very simple processing. We just flip it. What we do after flipping, we put it in the transmitter register, and since we enable the transmitter, it will be transmitted. Now, before doing this, we need to make sure that the transmitter is ready for us by stucking the CPU. We make it stuck in this while loop as long as the transmitter buffer is full. If it is full, keep in this while loop. If it is not, you will get out of this loop and then do the transmission. That's the way to do it. Notice in the pulling, the moment we receive, we were able to transmit. Now, what if we want to deal with the interrupt-driven I/O? We need to configure the UART same way we configure it in the bullet. The same statements. Again, you put it right there. I didn't put it because there is no space. More than that, you need to set the receiver interrupt and the transmit interrupt. And remember the three brothers that we talked about the interrupt, the flag, the priority, and the enable. The flag, we make sure it's 0. The priority is more than 0. Here we choose 2. In the receiver, we choose 3. So now transmitter priority is higher than the receiver priority. We can do it the other way around based on your choice. We enable the receiver. Now, if anything in the receiver, if there is something in the receiver buffer and the flag is on, it will interrupt the CPU and you start receiving. Now for the transmit, the flag is 0, the priority is 3, the enable is 0. We don't enable the transmit in our case here in this simple program. So we will only enable it if we receive something. So we need to enable this one. It's actually set by the receiver interrupt service routine. When you receive something, this one will be set and then you can transmit. Now in the main method, you would call the configuration. Remember, there are some lines here that is in the pulling. So we set up the mode register, we set up the status, and we enable the interrupts. Here you call this one, and you specify the baud rate, and you go through the while loop, doing other program code, doing something totally different. Only when you receive or transmit, it will be interrupted. It will be interrupted. Now, in the interrupt service routine themselves, we have 2 interrupt service routines, one for the receive, one for the transmit. If you check your book, there is many details regarding this, and even the codes are really big. I make the code very simple just to explain the idea. The purpose here is only educational purpose. So here in the receive interrupt, to go in this ISR, the event that will happen is setting up the flag of the receive. If the flag is there, it means that actually there is something in the you are receiving in the receive register. So you just make checking if the data is available. If there is a data available, then you take it from the register and put it in B. B should be globally defined. You could also make it local if you like, but I suggest you make it global because both of these ISR will work together. Now you clear the UART receive flag since you actually came here because it was set. So now you clear it. And after that, you could do some processing, some working with this. What I did here, I just enable the transmit. So now I set this transmit enable, and now I'm ready for transmission. Once the flag of the transmission is set, you will go in this interrupt service routine. You check if it is not full. You flip the value that was here, and then you put it in the register ready for transmission. Once you're done, you should reset the flag and also clear the transmission. I don't want to transmit anymore until I receive something else. This is a simplified way of showing the interrupt-driven communication in using the UART. A more realistic example is this shown to you here. This example is called ping pong double buffer. We have two buffers. One of them will be for receiving and the other one for processing. The problem is you have packets of bytes that are received through the UART1. So you are receiving something. And the median for each received packet is to be computed. So you compute the median, which is the middle value. Let's say if you have three values, let's say 1, 6, and 18. So the median value is the value in the middle after you sort them, which is 6. The median are accumulated and the result is output into 8-bit lit. So you need to calculate the median once you have certain values and you calculate their median. You get this median and accumulatively you sum up the medians over and over as long as you are receiving more packets. The solution here, we will use two buffers. We will adopt this idea. These two buffers, one for UART communication or the receive, and the other for the processing, which is here is the median computation. The buffer are alternated at each interval of the new packet, and the alternation is done through swapping the buffer pointer. So you have two buffers, or you can say arrays, and these arrays, each one of them has its own pointer. So you have two pointers, and then you swap the pointers when you want to do the ping pong. Swapping is doing the ping pong. Now, while we are doing this, we will explain it in a better way if we go through an example. Now, there is an essential condition for this to work. Now, the buffer processing time must be less than the time for receiving the buffer. So you are receiving signals, you should process them quickly. So you are ready for the new batch that you received. So the processing should be faster. That's the condition here. For the calculation or the processing here, it happens to be the median computation. And one requirement for the median computation, you need to sort the values first and then pick up the median. The sorting, we described it before when we talked about the C language for the microcontroller. And we talked about this idea. I'm just showing this to you so you remember. what we talked about. Since it's a sort, you need two nested for loops. And if the condition happen for the sort, you are sorting in an ascending order, then you need to swap the values. And we explained this table in the lecture, an earlier lecture, when we talked about the C language. Go back and check all the detail. So we need to do the sort in this problem when we calculate the median value. Now, to describe the ping pong behavior, let's see this example. Assume you are receiving speed is 1 byte per 1 millisecond. That's very slow, just for explaining the idea. The median computation, let's say it takes only 2 milliseconds. And the size of the packet, 3 bytes. Since it's 3 bytes and you are receiving 1 byte each 1 millisecond, for 3 bytes, you need 3 milliseconds. So to receive the batch that you need to calculate the median for, you need 3 milliseconds. And the processing is faster, which is only 2 milliseconds. That's the idea. And now the essential condition is satisfied. Now let's say that you have these data. One by one comes to you, one by one. And this data, the 3 will be in a single frame, the 8 in a different frame, the 1 in the next frame, and so on. So initially, you have two buffers. Each buffer is size of 3. But we'll say that this is the receiving buffer, and this is the processing buffer. At this point, we don't know what's the median value. There is nothing there. And initially, the accumulated sum of median is equal to 0. Now, the first data came to you, which is 3. You put it in the buffer, the receiving buffer. This is the time frame. This is at 0 millisecond, it's in millisecond. At 1, you receive the 3. At 2, you receive the 8. Now at 3, you will receive the next data, which is 1. And now you are ready because you have a full batch of data. And at this point, you can start doing the processing. Now, moving from here to here, we would do the ping pong, meaning now these pointers are changed, the receiving and the processing. Now this will be the processing and this will be the receiving of the new data. Now you will start doing the processing time and it will take 2 milliseconds, as you can see here. But while you are processing, you are actually receiving the next values, which is 7. So once you're done with the processing, at that point, you already received 7. And at this point here, exactly, sorry, it's at this 5, you will also receive the next one, which is 1. So you receive 2 in the receiving buffer, you receive 2 data, and you calculated now the median. Now the median value is 3, and you put it also in the sum. You're done with the processing. Now what will happen next? Since you already calculated this batch of data, it's wiped out, so you cannot see it anymore here. And also for the next millisecond, which here's millisecond number 5, this is number 6, you receive the last data and you would do the ping pong again. You see how fast is this now? So you will do the processing. And while you are doing the processing, actually you will receive more data. You're actually supposed to receive the 2 first here. So there should be 2 here, followed by the 8. Notice that you are receiving while processing, which is good performance-wise. And at this point, the processing time finished. You calculate the median value, you sort, and then you will find that the median is equal to 5, and you accumulately sum it with the previous 3. So now the value is 8. I should have mentioned here that also the median here after sorting is the median value is 3. You will have 1 first, followed by 3, followed by 8. So the median value is 3. And so on, you will do the ping pong again. So this will repeat itself more and more. This is very efficient. So you receive and process at the same time. So how to code this? Now you will have the longest code so far in the course. The idea is very easy. If you understand it, you can code it. Now we define the buffer size. Now instead of the 3 that I just explained to you, the buffer size is 10. You choose it based on the data that you are receiving. And you have a structure where you have the buffer array or the array of 10 members, since the buffer size is equal to 10, and you will have an index based on the current data that you just received. So initially it would be 0. Every time you receive a new value, it will be increased. Now for the reception, you prepare what you see here. You will define 2 buffers, buffer 1 and buffer 2, and you will prepare also 2 pointers. One will point for the first buffer, you make it the receive buffer, and the other is the processing buffer by pointing to it using the processing pointer. You also define a semaphore called the new packet received. Once it is activated, it means that you already received a packet and you need to process it. Here, just in case you are busy with processing, this is a flag for that, processing active. So you don't want to have a lot of reception and you are still slow in processing and still active, you are very slow. This will cause troubles for you, and this flag will be helpful to you. We will see how to use it. We configured LEDs because we want to show up this sum. So we chose TRIS or port B for that. We make the 8 bits or the least significant 8 bits or the least significant byte for that. And we also disable their analog values. We set up the GPIO in the previous lecture, same thing here. And also we have here an update LED method. If you have a new value, you would update the LEDs based on this new value. Which basically the previous LED B now will be overwritten by the new value. Now in the main code, what we will have, we will initialize the receiver and the semaphores. So we have the receiver buffer index, we make it 0, it's empty now. And we point to it by the receiver pointer. So the receiver pointer is the address of the first buffer. For the next one, we make the index also 0. There is nothing there for processing. So the processing pointer have the address of the second buffer. And we make both the semaphore, the new packet received, equal to 0, nothing there. You're not receiving anything, and the processing is not active, so the processing active is equal to 0. We initialize the sum. You could have initialized the median too, but we don't really care because once we receive something, we will work on it. We configure the LEDs, or we call the configurations here. We configure LEDs here. And we configure the UART interrupt, and we give it the baud rate. This is actually what we specified in the bullying method. Or actually also the one in the interrupt, since we are using the interrupt one. Now here in the while loop, you just check the semaphore. The idea here to make things simple, we identify or we initialize the new packet received semaphore for this purpose. If it is equal to 1, which should be set by the interrupt service routine, if it is equal to 1, then you make it 0 and you calculate the median. Basically, you sort and pick the median, and then you accumulate the sum with the current median and update the LEDs based on that sum. So that's fairly easy. Notice that we are calling this method, which is process the received packet. This method will do the sort that I just mentioned. sort, and then pick up the median. And then it will return the median. But before this, we should work on the process itself. Or sorry, in the receive itself, when we receive the frames. So the idea here is to receive and put it in the buffer. Receive and put the frames that you received or the bytes that you received in the buffer. To do this, we have the we use the interrupt service routine method. We have the U1RX interrupt ISR. It will be set, or it will be called. I don't want to use the word call actually, because it's associated with the event, and that event is there is something you received in the receive buffer. Once you have received something, you need to handle it in the ISR. You go here. There is some initialization. One of the important things, and one of the job of the programming is to set clear this flag. Actually, when this flag is equal to 1, you go through the ISR only at that event. So now we clear it, and we need to define a temporary or we need to define a receiving index. The idea here is to whatever you receive, you put it in the buffer. So we identify this one here, or we define it. It's called receive index, which is I make it to equal to the same value of the pointer index in the current time. If it is empty, it would be the index here is actually a 0. So once I have the receive index, now I can use it just to make things easier to read in the code. RX index, we have the index here. And now you access the buffer by its pointer. And then whatever you are receiving, you put it inside the buffer and you increment the value of the index. So now you actually put it in the buffer. Now we have what you see here in the if statement. If the index is equal to buffer size, it means now it's full. The buffer with its 10 member is full and you cannot receive any longer. It also means the batch that you need to calculate the median for is ready, and now you can go and do the processing. So now you check if the processing is active. So now you have the batch, but the processing is still active. This is trouble. So you need to do something about this. Now the buffer processing is greater than the buffer receive. So you need to do an action. For example, you halt the processor, you wait a little bit of time, you say that it's failing and you need to work something out. Now, if not, meaning the processing active is equal to 0, and now you can do the processor because it's 0, you can initiate a new processing. You do the ping pong, and you do the ping pong easily by swapping the pointers only. So you need to define a new pointer. It's a temporary pointer to do the swap. So you put the receiver here, and then the processor pointer instead of the receiver, and whatever in the temporary pointer, you put it in the processing pointer. We just did a swap, and we explained the idea of swap before. And at this point, and I told you that our semaphore should be set by the interrupt service routine. Now you say a new packet is received is equal to 1. So now this is the semaphore. It says that the new packet received is equal to 1. Which means, going back in this previous slide, the new packet received is equal to 1. And now you should do the processing. You should do the processing. Now, processing the received packet, I explained to you what to do. It's also written here. To process the received packet, you just say here that just set the flag. So in case this problem happened to you, you can catch it. So you set the flag, the processing is active. Once you're done, you make processing active to 0 for the next batch. So here what we did, we have the two for nested loop with a condition and then a swap. So what you are doing here is actually sorting the value in the buffer. Remember, we already did the ping pong in the ISR. So now we do the processing. Once it is sorted, you pick up the median by this simple method. Just you go to the buffer and you find the median value by the buffer size divided by 2 to pick up the median. And now you return the median. But before that, you wipe out the buffer. Since now you have 10 members in the buffer, you sort them, you pick the median, you're done. Make the index 0 and finish the processing. So now you are ready for the next batch and you return the median value. That's simply how to do it. At this point, you know how to work with the UART, how to use its special function registers, how to set it up, how to do the transmission and the receiving. You could see from this example that the receiving is actually more important. When you receive something and you work with it, also it's very important to send. It's a communication module. At the end, I just want to mention the BIC24 microcontroller to PC serial I/O connection. Just know that sometimes there are differences in the voltage or the voltage ranges. So be aware of this. So our USB to serial cable use CMOS voltage levels. The other cable may use the RS-232 voltage levels. So we have two different voltage levels, the CMOS voltage levels, which is this one, logic 0 for 0 volts, logic 1 for VDD. And this is done in BIC24. So logic 0 would be 0 volt, the logic 1 would be kind of 3.3 volts. That's how we know it in the microcontroller. The RS-32 voltage level is different, something different. So you need to convert between this and that. So for the RS-232 voltage level, logic 0 is considered from a plus 3 volt to 25 volt. While logic 1 has a negative value from minus 3 volt to minus 25 volts. So we need to convert for things to work. To do the conversion, we use this chip. It's called MAX 3232. It just do the conversion. So whatever values that you are sending or receiving from the RS-232 cable, the microcontroller would read it correctly because you did the conversion using this chip. So usually you have a PC or a laptop, you connect it using the RS-232 to a certain port, and we said that we care only about 3 terminals, which is the receiver, transmitter, and the ground. The sender and the receiver will be connected to the receiver and the transmitter of the MAX 3232, and the ground will be common between both chips. And you can see that they will be converted. There are so many details here that we took out, and then the microcontroller will be ready for it. Of course, the transmission will happen this direction, and the receiving after whatever processing you do here will be in this direction. At this point, we finished the first communication module, which is the UART in BIC24. And next, we will move to another communication module. It's called the SPI. Once we talk about the SPI communication module, also we will show how to use it, how to use the SPI with the external memory or with the serial external memory, which is the EEPROM. We will see that next. Just to connect all the dots together, we already talked before about the parallel memory. when we move to the SPI communication module, we will talk about the serial memory. So I'll see you next time.